Wu Shenshuang was born in Suzhou, China on May 31, 1912. Wu's father had very progressive ideals and encouraged Wu to receive a good education just like her brothers. Wu attended National Center University in Nanjing, where she received her bachelor's in physics in 1934 and graduated at the top of her class. After graduating, Wu worked for Professor Jingwei Gu, who earned her PhD in the United States and encouraged Wu to do the same. In 1936, Wu moved to the United States and decided to pursue her higher education. Initially, she planned to study at the University of Michigan. However, upon arriving to California, she was immediately drawn to the facilities at the University of California, Berkeley, and decided to study there instead. Also, she learned that in Michigan, women were not even allowed to use the front entrance, which further solidified her decision to stay in California. Wu studied under the supervision of Ernest O. Lawrence, the Nobel Prize winner for physics, for his invention of the cyclotron particle accelerator. Wu's thesis consisted of two parts. Part 1 of her thesis was on bremsstrahlung, which is the electromagnetic radiation produced when a charged particle deflects off another charged particle and slows down, which happens when an electron collides with an atomic nucleus. Part 2 of her thesis is about the production of radioactive isotope xenon by the nuclear fission of uranium. Wu received her PhD in June of 1940 and remained at the Radiation Laboratory of UC Berkeley as a postdoctorate fellow. In 1942, Wu married and moved to the East Coast with her husband and began teaching at Smith College. Then, she moved on to teach at Princeton University as the first female instructor ever at the institute, and worked as an instructor for naval officers. By this time, World War II is raging in Europe and the Pacific. In March of 1944, Wu joined the Manhattan Project Substitute Alloy Materials Lab at the Columbia University, which supported the Manhattan Project's gaseous diffusion program for uranium enrichment. She helped develop the process for separating uranium into the isotopes uranium-234 and uranium-238 through gaseous diffusion. This process was scaled up for the production of uranium to be used in atomic bombs. After the war, Wu began working on problems surrounding the principles of nuclear physics at Columbia University, where she would remain for the rest of her career. She became a full professor in 1958 and the first woman to hold a 10-year position in the Columbia Physics Department. Wu also continued researching beta decay, which is when a nucleus of an atom has too many protons or neutrons, and one of those protons or neutrons transform into the other. In 1934, Enrico Fermi had published his theory of beta decay, but another physicist by the name of Luis Walter Alvarez was creating the experiment and getting different results. Wu quickly understood that Alvarez was seeing different results due to a setup difference, where the magnetic spectrometer used by Alvarez contained an iron core that produced a heterosis effect and caused the experimental error. She performed the experiment with an iron-free solenoid spectrometer and showed unambiguously that the Fermi theory of beta decay was correct in all its details. In the mid-1950s, Wu began working with two other Chinese physicists, Cundao Li and Chen Yang, to study the law of conservation of parity and elementary particle physics, which would prove to be some of her most notable works. Parity is a mathematical operator that acts as a mirror. If we have a coordinate system, parity will flip only one axis, or it will flip all three axes. Ultimately, scientists were interested in knowing whether the mirror image of a universe is identical to our own universe. That is, whether our universe conserves parity. So, how do we quantify parity in a physical system? In quantum mechanics, the wave function equations represent the physical state of a particle. Mathematically, parity reflects the spatial proportions of the wave function through the origin, which is the equation shown. Using this notion of parity operator, different types of particle can be assigned different values of parity based on the nature of their wave functions. The bottom equation is one that is most important to the understanding parity violation. For a system composed of many particles, The total parity is the product of the parity of the individual particles with a factor to account for its relative motion. The validity of parity symmetry was thrown into doubt by the discovery of two particles, theta and tau. Tau was observed to decay into 3 pions, while the theta particle was observed to decay into 2 pions. The pion has a parity of -1, so by using the equation from the last slide and assuming parity conservation, it can be shown that the tau has a parity of -1, while theta has a parity of 1. The problem, however, is that the two particles have the exact same properties, including mass, spin, and lifetime. These two decay modes were of opposite parity, meaning that parity was not conserved, further implying that reflection symmetry was not obeyed. Li and Yang has been researching particle interactions and found that parity was conserved for electromagnetic and strong interactions. The two scientists predicted that, however, there was no evidence that the conservation of parity would hold for weak interactions, and the scientists immediately invited Wu to carry out the experiment. The experiment carried out by Wu involved the beta decay of cobalt-60 into nickel, an electron, and an electron antineutrino, the process which involves a weak nuclear force. The cobalt was placed in a solenoid magnetic field to align the atom's magnetic moment with the direction of the field. The cobalt was then allowed to decay. If parity is conserved, electrons should be emitted equally in both directions. However, reflecting the process in a mirror, the exact same process will occur, with only the magnetic moment of the cobalt rotated by 180 degrees. However, Wu observed that the electrons were preferentially emitted in the direction opposite to the cobalt's magnetic moment. If the process was reflected in a mirror, we see that parity is violated because the electrons will be preferentially emitted in the direction of the moment, contrary to the direction of emitted electrons observed by Wu. Wu's findings was confirmed by two other groups of physicists, quickly confirming the breaking of the parity in weak interactions. Parity violation was a huge deal in the world of particle physics and played a significant role in the development of the Standard Model, which is a theory that describes 3 of the 4 known fundamental forces in our universe: weak, strong, and electromagnetic interactions. The Standard Model also played a role in the classification of elementary particles. Although the significance of Li, Yang, and Wu's research were immediately recognized by the physics community, only Li and Yang were awarded the Nobel Prize for this discovery. In fact, Wu's contribution in the discovery was not publicly honored until she won the Wolf Prize 23 years later, in 1978. However, Wu's research didn't stop after her parity triumph. She investigated and confirmed the conservation of vector current hypothesis in beta decay in 1963, confirmed the calculations on the correlation of quantum polarization of 2 photons propagating in opposite directions, and researched the molecular changes in the deformation of hemoglobin in sickle cell anemia. In her later years, Wu also began to speak out on social and political issues, especially on equality for women in science. At the MIT Symposium in 1964, while speaking about professional discrimination against women, she said, "I wonder whether the tiny atoms and nuclei, or the mathematical symbols, or the DNA molecules have any preference for either masculine or feminine treatment." On top of her numerous awards and honors, Wu was the first woman to win a Research Corporation Award in 1959, became the first female president of the American Physical Society, first person to win the Wolf Prize in Physics, first living scientist to have an asteroid named after her, and undoubtedly, Chien-Shiung Wu is truly deserving of the title, the First Lady of Physics.